Hello friends, welcome to my channel. In this class, I will discuss about the flow work for a control volume. What is control volume? Control volume is same as open system in which there is both mass and energy interaction between the system and surroundings. So both mass and energy interaction can take place. That means mass can flow across the system boundary either into the surroundings or from surrounding towards the system. So mass interaction can take place. So that's why that open system is same as a control volume. So what is actually flow work? It's a type of work. What is that? And this happens only in case of flow process or open systems, and not for closed or non-flow systems. So what is that we will discuss. And control volume is nothing but open system. They are same things. Control volume is same as open system and control mass is same as closed system. So before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. You see, first we will discuss what is flow work and what is the energy of a flowing fluid. Suppose there is certain amount of fluid inside a system. This is suppose open system, or you can say control volume. Suppose this is a fluid element, that this is the boundary and this is the control volume. So this fluid when enters into this control volume, some fluid has to push this into the system, into the control volume. How can this fluid element enter into control volume? Another fluid which is upstream to this fluid element will push this fluid so that this fluid can enter the control volume. Similarly, here also at outlet or exit, this fluid element pushes this fluid, the next fluid element, that is downstream, so that this can leave the system. So in both the cases, some work is needed to push the fluid either into the control volume or out of the control volume, and that work is known as flow work. Suppose these elements, this small element that we will take that for analysis, suppose this pressure is of that fluid element is P and volume is suppose V, and mass of this small fluid element is suppose M. And you see, this can be considered to be the fluid element upstream to this element can be considered to be an imaginary piston. Just like in closed system, what happens? A piston pushes the gas in case of a closed system. Similarly, this upstream fluid element which pushes this fluid element and enables it to enter, give the required force to enter this control volume, can be considered to be an imaginary piston. So we know that when suppose this distance is suppose L, this fluid element moves through a distance L, and the force here is P into A, pressure into area. What is that pressure? This is suppose here the pressure is exerted at this pressure at this section. Suppose the pressure exerted by the fluid is P, and cross sectional area of the fluid element is suppose A. Then the force exerted by the fluid is how much? P into A, pressure into area. So this fluid has to exert and force in opposite direction to overcome this force, so that the fluid element can enter into control volume. So this fluid element, upstream fluid element that pushes this fluid element into the control volume, has to do some work. So to move a body, we need to do some work on it. So in this case that happens. So this upstream fluid element does some work upon this next fluid element, so that this fluid element can enter into control volume. and that work done will be, this is the pressure into area is force, and work done is nothing but force into displacement. Force into displacement, that is force multiplied by L. L is the distance through which the fluid element, this fluid element moves because of the force that is applied by the upstream fluid element. So suppose this fluid element passes through a distance L, then work done is nothing but the product of force into displacement, F into L. So I can write this PA into L. So I can write P into the volume. A into L when multiplied results in volume. Pressure into volume. So this work is called flow work. Flow work. So I can define flow work as the amount of work, or you can say the work amount of, or you can say the flow work is the work. Flow work is the work required to maintain continuous flow of fluid into system. And here at the exit end also, this fluid element has to push this fluid element so that this fluid element can get out of the control volume here at the exit end. So here the work is done by this system, because here the work is done by the fluid inside the control volume, but in this case the work is given to this fluid element from outside. That means here work is done on the system, and during calculation this work will be considered as negative, because according to convention, when work is done on a system it is called negative, and work is done by this system it is considered as positive. So this PV, product of pressure and volume, and that is called flow work. But if you calculate work done per unit mass, if you calculate work done per unit mass, suppose this fluid element, this element has mass m, that means work done per unit mass, this is the total work done on that element of mass m. But if you are to calculate work done per unit mass, that will be P multiplied by V divided by m, where m is the mass of that fluid element. This will become P into specific volume of the fluid. Specific volume, pressure is a property of fluid, and specific volume is also property of fluid, and this work done per unit mass, which is needed to maintain the continuous flow of the fluid into the control volume, is called flow work. And some people argue this as this is not flow work, this is flow energy, because this is a combination property, pressure and volume, pressure multiplied by volume, just like your enthalpy is a combination property. Similarly, this is also a combination property, or that's why they argue that this is kind of flow energy. And there is no end to this conversation of whether it is flow work or flow energy. But as far as the calculation of energy balance equation is concerned, it will have no impact. So it may whether it is flow work or flow energy, it does not matter. So for the calculation of point of view, it remains same. So anything is acceptable, whether flow work or flow energy. So next will and the value remains same, whether while you calculate this flow work at the inlet or outlet, the value remains same, and that value is nothing but the product of pressure and the specific volume of fluid. And then total energy of a flowing fluid, total energy of a flowing fluid, total energy of a flowing fluid. In case of closed system, we have already calculated that the total energy of a closed system is sum of these three energy. U is the molecular internal energy, then kinetic energy, then potential energy. And for specific for unit mass, this energy will be specific internal energy, and that is half v square, because half mv square when divided by m results in half v square, plus gz, where the z is the reference, z is the height of the body above a arbitrary reference point. So this is the specific energy of the fluid in case of a closed system or non-flow system. Closed system is same as non-flow system because there is no mass interaction between the system and surrounding, no mass flow takes place there. So this is the total energy, and it can be denoted by small e also, that can be written like this. This is the specific energy of a closed system. If you want to calculate the specific energy of a flowing fluid, this will be nothing but specific energy of a flowing fluid will be, maybe it can be denoted by theta, and that is nothing but U plus, you can add PV because this is the flow energy. This energy or this work is required for maintaining the constant flow of fluid into the system or out of the system, into the control volume or out of the control volume. So this term will be added. This is for flow work, and this will be there only for flow system, not for non-flow or closed system. Closed system, total energy summation of three energy, U plus half v square plus dz. This is specific energy of a closed system. Energy divided by mass is specific energy. But for open system or control volume, this term will be added because this is the flow work per unit mass. Then all other things will remain same, v square plus gz. You know, U plus PV is nothing but the summation of U, specific internal energy, and product of pressure and specific volume is nothing but the specific enthalpy. Specific enthalpy whose unit is either kilojoule per kg or joule per kg, plus half V square plus Gz. This is the total energy, total specific energy of a flowing fluid, which is denoted by theta. And this is summation of these three things: H specific enthalpy plus half V square specific kinetic energy and specific potential energy. This is the total energy of a flowing fluid, and this is per unit mass. This is nothing but total energy of a flowing fluid per unit mass. And total energy of a fluid of a non-flow system will be U plus total energy per unit mass in case of non-flow system will be like this. This is the difference. And in case of flow system, H will be there in place of U, and this H simply takes care of the flow energy or flow work and nothing else. So once you take enthalpy into consideration, your flow work concept is taken care of. So there is no problem, nothing to be worried about flow work once you have taken the H into account. So this energy transport, if you want to calculate, suppose at the inlet, suppose the mass flow rate is, suppose this is the boundary, and the mass flow rate is mi dot. That means mi dot means rate of mass that enters into the system. That is, unit is kg per second. And what is the energy transport by mass? This is applicable, for a closed system only energy interaction across the system boundary takes place in the form of heat or work. But in case of flow system, apart from this heat and work interaction that takes place across the system boundary, some other energy transfer or energy transport may take place in the with the mass that enters into the control volume or the mass that leaves the control volume. So there is also energy interaction across the system boundary in case of a control volume or open system with the mass entering into the control volume or the mass leaving the control volume. So that's why this is called energy transport by mass. This energy transport by mass. Energy transport by mass. This energy transport by mass is calculated for energy balance in case of a control volume, not in case of a non-flow system or closed system. This is applicable. Energy transport is there only for flow system or a control volume, and this energy transport is nothing but the product of mi dot theta I. Theta I is the total energy of a flowing fluid, as I discussed. That is, if you calculate this per unit mass, theta I का unit of theta I होगा kilojoule or joule per kg, and the unit of this mass flow rate is kg per second. So on being multiplied, whatever unit will be kilojoule per second or kilowatt. So energy per time you will get. Energy transport by mass, whatever energy is transported into the control volume with the mass can be calculated like this: mi dot rate of mass that enters into the system, and theta is the energy transport by mass per unit mass. Theta I stands for energy transport per unit mass. And when the mass leaves the system, that will be me dot. This is the mass flow rate that leaves the system multiplied by theta E. This is the energy of the flowing fluid. Energy of the flowing fluid at exit end. Me dot multiplied by theta E. So unit of this will be kg per second multiplied by kilojoule per kg, and again that will be kilowatt. So this expression mi dot or m dot, overall I can write m dot theta. M dot is for mass flow rate, theta is the energy, specific energy of a flowing fluid or energy of a flowing fluid per unit mass. So this calculation can be useful while deriving the energy balance equation for a control volume, and for a special case, first case of steady flow, that equation will be known as steady flow energy equation, which we will discuss in the next video. So that's all.